Hello, my wonderful students in grade 8. This is Ghassan Masada, a science teacher at Taqarrub International School. I hope that all of you and your families will be well. Today we will complete the discussion of gravitational force and how we can measure the force of gravity from page 88 to page 93. In your book there is a lab on page 87 and 88. Unfortunately, we cannot do it now experimentally. But we need to learn how we can find the gravitational acceleration. As we know, the Newton's second law states that the force on an object can be found by multiplying mass by acceleration. In mathematical form, we can write it as F is equal m times a. And when we need to calculate the acceleration, rearrange this formula to write it in form a is equal F over m. When we apply this formula to a force of gravity that effect on an object with mass m, we can find the gravitational acceleration. Always, the ratio between force of gravity and object mass is similar and does not change with mass. Even if the mass of an object increases, the force of gravity between the object and Earth will also increase by the same amount. Close to the Earth's surface, the acceleration of any object is about 9.8 meters per second square, and it's called the gravitational acceleration and indicated as g is equal 9.8 meters per second square. Now we will describe new things. New things is called weight. Weight is the gravitational force exerted on an object by Earth. And because weight is a force, it's measured in newtons. Near Earth's surface, the weight of an object in newtons is about 10 times its mass in kilogram. The weight of an object can be calculated by using the following equation. Weight is equal mass with mass measured in kilogram times the gravitational acceleration, which is measured in meter per second square, and the weight is measured in Newton. Or we can write it as weight is equal mass times g, where the g is the gravitational acceleration. From this explanation, we can conclude there is a big difference between mass and weight. When an object is at rest on a surface, such as a pencil on a table as shown in this graph, the normal force on object is equal in size or magnitude and opposite in direction of the object weight. And in this graph, we can see the free body diagram for this object. So when we have a pencil on a table, we have the gravity force or the weight for this pencil to the down, and here we have the same magnitude of the force, but in the opposite direction. This force is called normal force. And this is the basic idea for Newton's third law. For any action, there is a reaction in the opposite direction, but with the same magnitude. For example, what is the normal force on a 10 Newton weight sitting on the floor? The idea for this example, it's the F normal must be equal the F for the gravity, and with this meaning the F normal is equal 10 newtons. Now, please open your book on page 89 because we want to solve some examples. For each of the systems below, calculate the weight of the object, then apply scientific understanding to draw a free body diagram of the system. Part A. A book with a mass of 2 kg is at rest on the top of the disk. We need to calculate the weight for this book, and we need to draw the free body diagram for this system. The weight for this book, to calculate the weight, we can use the weight equation, where the weight is equal mass times g, where g the acceleration of gravity or gravitational acceleration, and is equal approximately 10 meter per second square. Substitute the numbers, we can the weight for this book is equal 2 times 10, which is equal 20 in newtons. And for the free body diagram, we can draw it as shown in this figure, because this is the object or the book, and the gravitational force to the down, we have the same magnitude but the opposite direction of normal. Example B, a pencil with a mass of 0.0075 kg is falling down the floor. Also, we need to calculate the weight and draw the free body diagram for this pencil. To find the weight, use the weight equation, where the weight is equal mass times g. Substitute the numbers, we can find the weight, where the mass is equal 0.0075 times 10. The weight is equal 0.075 in newtons, and we can draw the free body diagram as shown in this figure. In this case, the pencil is falling, so there is only one force acts on this pencil, which is the force of gravity. On the top of page 90, you have a three-dimensional thinking. Construct an argument on whether the weight of a pencil would change as the pencil falls from 10 meters to the ground. Please stop the video for 2 minutes and try to solve it. The best answer is the weight is determined by the gravitational force on the pencil. Near Earth's surface, this force is the same, so the weight would not change as the pencil fell. The last thing in this lesson, why are small objects not attracted to each other? For small objects, mass such as pencil and book are very small compared to Earth mass. So the gravitational field is very small. They pull in each other, but not enough to cause a change in motion. Finally, read this paragraph on page 91. Read this paragraph carefully. And the last thing, we will do the lesson review on page 93. Open your book on page 93 to answer the questions number 3 and 4. We have a three-dimensional thinking. The model below represents a star orbited by two planets, planet A and planet B. The star is also orbited by the mysterious object X, which is entered into the star's gravitational field. The star is the most massive object, followed by planet A, planet B, and object X. Use the model to answer the questions 3 and 4. Question number 3. In the model above, how is the mass of the object represented? The mass is represented by the size of the object. The mass represented by the distance between the objects. The mass is represented by the color of the objects. The mass is not represented. The correct answer is A, because neither the color or distance correlates to the relative masses. Any question number 4? The gravitational force from planet A on the star is shown in the model. How should the arrow that represents gravitational force from the star on planet A be represented? It should point from planet A toward the star and will be longer because the star has more mass. It should point from planet A toward the star and will be the same size because it is an equal and opposite force. It should point from planet A toward the star and will be shorter because planet A has less mass. There is no an arrow to represent because the gravitational force is only in one direction. Thinking about the best answer, the correct answer for this question is B, because the gravitational force between two objects are equal in magnitude but opposite in directions. I will stop at this point. I hope we can meet together and we are all fine. Don't forget to solve the worksheet attached. Thank you very much, my students in grade 8.